Section 12.6 is a very important section. We're going to graph in 3D, and we're going to leave that alone for a bit, and then we're going to come back to it heavily in chapter 15 and mainly 16. So it's very important for you to really familiarize yourself with the graphs. If you look in the section 12.6, there's a page that has a list of graph you should familiarize yourself with. I tried to make the graphs matching the y-x plane, meaning when you see, remember, this is the y, this is the z, and this is the x, meaning when you see z equal in 2 dimensions, that's like y equal, and since that's the y equal mx, that's z equal my. Anytime you see z and y, think of the traditional 2 dimensions. So when you see z equal y squared, that's like saying y equal x squared. We know what that graph looks like. Now, GeoGebra.org is a place for you to really practice those graphs, to see them in 3D. On the test, however, if I give you one of those, I need you to graph it by hand, so familiarize yourself with this. Z equal y squared is a graph normally that looks like this. In 2 dimensions, that's fine. In 3 dimensions, you'll notice there's no x. Anytime x is not present, or a variable is not present, that means you're going to trace this graph along that axis. That means z equals 0, you will be right there. Z equal 1, z equal 2, z equal -1, and all what you have to do is kind of connect the back together and the front together, and there it is. The actual graph from GeoGebra looks like this. So I'm going to show you, this is accepted on the homework. GeoGebra gives you that graph right there, and I want you to practice. You don't have to get a perfect graph, but you need to be able to identify a graph if I gave you the graph, and you need to be able to sketch it or describe it. So I notice this passed through the origin. If I look at A and B, the difference between A and B, I notice that's like saying y equal x squared plus 2. That's a parabola shifted up 2 units. So I go up on the z-axis, because when y equals 0, I'm right there, and I sketch that graph again. Oops, that graph again, a parabola. But now I'm along this line. I sketch another one of those, and maybe one more. Connect the back, connect the front, and there's the graph. So it's kind of like a sheet of paper that you actually just bend over. And let me show you what that looks using GeoGebra. Let me get that graph. And in GeoGebra, the graph looks like that. By the way, if you go to GeoGebra, you have to really rotate the axis. I'm going to show you one really quick. Okay, so I'm going to go to that website really quick and show you. There's the site. If you just Google it and hit the 3D graph, on the left hand side right there, I'm going to input the equation. Right there. I'm going to put the equation that I need, and you could see the graph. For example, z equal y squared. There it is. But you notice this is the z. You notice that this is negative and this is negative. You just click, right click, and rotate, and there it is. That's really how you want to look at it. The green is always the y-axis, the blue is the z, and the x-axis is coming out at you. Now you could rotate it a bit and see how it looks. and you could go to 2 dimensions and see how that looks as well. So I suggest you play with that a bit. And there it is. Now let me just put this back where it was. And there it is. Now I want to go to z equal 1 minus y squared. So I know how that looks. That's like saying y equal 1 minus x squared. That's a parabola. If I go up 1 unit, and it's going to be traced along z equal 1. So along z equal 1, if I sketch that graph again, and the back is kind of hard to see, it's in the background, and that graph, using GeoGebra, it looks like this. So visualizing the graph is a lot more important than the actual graph. You're going to have to find the volume in chapter 15 and 16, and you really just need to picture what that graph look like. Now if I look at part D, I notice if I set this equal to 1 just like I do normally, right? So if I divide by 9, I'll be looking at x squared over 3 plus y squared over 9 equal a 1. Actually, let me get rid of that. So normally if I look in the xy, there's the y, there's the x. If I look in the xy plane, I'm going to move radical 3 in the x. So 1, 2, 1, 2. And I'm going to move 3 in the y. And on the floor, that looks like this. Kind of like saying, move radical 3 in the x, 3 in the y, and normally you would graph an ellipse. That's what this is. Keep in mind that this x-axis is actually right there, and the y-axis is right there. Now, since there's no z, this graph is gonna trace along the z-axis. It's really a cylinder in 2 dimensions. That is, means if you look from the top down, you would see just the ellipse. This is all infinite. That never ends, never terms. Same with those. All of these are infinite. And I'm gonna get the graph from the GeoAlgebra in a minute. And there it is. Again, if you glance at this, this is the x, this is the y, and this is the z. You'll notice there's a more stretch along the y than there is along the z. We know that already. I'm sorry, there's a more stretch along the y than there is along the x. Now, if I look at the next problem, z equal, again, I'm picking those so you could see them. That's like saying y equal the cosine of x. Well, I would go up 1, down 1. A graph of a cosine starts on the amplitude. It runs down, back up. But then there's no x, meaning this graph is going to trace along the x-axis. So you sketch this again. And just connect the likes together. And there it is. And if I use GeoAlgebra, it looks like oh boy. Okay. Okay, the graph looks something like this. Kind of hard to fit all of those in, but there it is. And you notice it starts at 1 and it runs all the way in. Now the next graph, if I look at anything that has all three of those, I'll see if I could solve for one of those. And here I do notice that I could move the y to the other side and say y equal 4x squared plus 4z squared. Now I go by, first, does the graph pass through the origin? That is 0, 0, 0 a solution? In this case, it is. The graph passes through the origin. That's a big deal for me. I will cover the z. Y equal x squared is a graph that looks like this. X equal 4, y equal 4 x squared is a graph that looks like this on the floor. And if I zero out the z, if I zero out the x, y equal 4z squared is a parabola that is wrapped around the y axis but running in the z direction. So this blue graph is on the traditional y z plane, and if you connect, you go from one color to the next, you will able to see how that graph look like. This is a paraboloid wrapped around the y-axis. And let me get the graph from GeoAlgebra so you can see how it looks like. And that's what the graph look like. There's the y-axis, and the graph is wrapped around it. When we meet in class, you could ask me, I could take a trip there and show you when you ask questions. I will be doing it by hand first, then show you how that looks using that software. This problem right here, if I really look at this, that looks like if I divide by 12, so I do normally what we do in 2 dimensions, divide by 12, set it equal to 1, x squared over 4, plus y squared plus z squared equal a 1. What that means, 0, 0, 0 is not a solution. This graph doesn't pass through the origin. Now, if I cover 2 of those, that is, if I cover, let's say I cover x and y, I know z is between 1 and negative 1. If I cover x and z, y runs between 1 and negative 1. And if I cover y and z, x runs between 4, between 2 square root, right, and negative 2. So on the floor it looks something like this. And there it is. If I make that a bit circular, it will look a bit better. Maybe make the axis rotate a bit more. Okay, maybe like this. So as we said, I will go 1 and negative 1, 1 and negative 1. It looks like a circle in the YZ plane. But along the X, you really move 2 and negative 2. Something like this. There. And of course the GeoAlgebra will give you a better graph. That's really what it looks like. I'm trying to mimic that. So again, the graph doesn't have to be perfect, but you could, if I say explain what that means, you should be able to explain it the way I just did. And if I look at this graph, I do notice that 0, 0, 0 is a solution. This graph passes through the origin. Now if I zero one of those out, that is, if I look, since z is not squared, I could say, look, z equal negative 2x squared minus 4y squared. So if I cross out the y, this says z equal negative 2x squared. It is in the x z plane, and it looks something like this. Imagine that's really coming out of the page and into the page. If I zero out this, z equal negative 4y squared, that's going to open in the traditional xy. It's going to be steeper. And to see it, you have to go from the blue to the green, to the blue to the green, and back. That's really how it looks like. I'm going to get the graph from GeoGebra and show you how that looks like. And if I look in GeoGebra, that's really what I get. You notice it's the same thing. There's the x, there's the y, and there's the z. The good thing about GeoGebra, you could rotate it and see really what it looks like from the top, the bottom, and the side. This is one of the toughest graphs to do. This is a saddle. And if you have a hard time graphing it, this is the one graph I have a heck of a time sketching. But if you just tell me that it is a saddle on a test, I'll accept, because in applications you need to know what that means. And I notice the graph passes through the origin, but if I zero out the y, x equal y squared is a graph that looks like this. But if I zero out the y, z equal negative, the x equal negative z squared is a graph that's going along up and down. Now here's the tricky part. You need the blue to trace along this, and the green to trace along this. And that's why it's so hard. It's literally a saddle. And the graph really look like this. It's very hard to do. So you telling me it's a saddle is good enough. Make sure you identify that, because in applications we're going to find maximum and minimums. It's very important to know it's a saddle, because that indicates that there is no maximum or a minimum. If I get to I, again there's a negative, so I'll say, okay, well, I could really move that over. It is 4x squared plus y squared equals z squared. Now you notice, if I zero out this, if I zero out the x, in the y z plane, this says z equal plus or minus y. Well, z equal y and negative y, there it is. Now if I zero out the y, this says z equal plus or minus 2x, a line coming along the z x. I should have used the lines. Let me just fix it right now. I can do that. Here we go. So y equal x, y equal negative x, and y equal z equal 2. I said y equal z equal y, z equal negative y, z equal 2x, and z equal negative 2x, and the way to see it, you would connect from the blue to the purple, to the blue to the purple, and back. So this is what we call a double cone. And let me get the graph from GeoGebra so you can see what it looks like. And that's what the graph looks like. You'll notice it's a cone, but it's not a solid cone, because there's more stretch along the y than there is along the x. In the x it's steeper, because z equal, kind of like me saying y equal x, you say, oh okay, I know that cuts at 45 degrees, but y equal 2x, is a line that's steeper. So that's something just you have to kind of visualize and practice. And I know you're going to have a lot of homework questions. When we do those, I will elaborate. Now, when I look at the following graph, I notice here I could solve for z. Anytime you could do that, that's good news. Z equal 2 minus x squared minus y squared. So you notice here, the graph doesn't pass through the origin because 0, 0, 0 doesn't work. Right? If I let x equal 0, y equals 0, z equals 0, 0 equal 2 doesn't work. Well, if I cover the y, this is along the zx plane, 2, and opening left and right. If I zero out the x, this is along the yz plane, traditional xy plane, and z equal 2 minus y squared. Sometimes you have to go a bit further than you should just to see it. And the way it works, you're going to run from the purple to the green, to the purple, to the green, to the purple. So paraboloid opening downwards, that's how the graph looked like. And if I look at the last graph that I have, I'll notice if I zero x out, this is a circle in the zy plane. So that is 1, 1, 1, 1, 1, 1. It's a circle right there. Now, if I zero out the y, z squared minus x squared equal 1, that's a hyperbola in the z direction. It's going to come out, so you imagine the x and the z. It's coming out and coming down. And if you zero out the z, you notice that's a yx, but it's going to be wrapped, it's going to open along the y-axis because there's a negative in front of the z. So this is going to follow this way and this way. I really messed up. Let me do it again. The graph looks something like this. A bit harder to see, but if you know what it looks like, then you could pretty much. The important part is I know there is a circle in the xy plane, in the zy plane, and from there and again, anything that runs along the x-axis is kind of hard to see because it's kind of like coming out at you. So you need to practice those a bit. You know, probably you're better off once you know what you're doing. There. That's kind of how you do it, and then you add the axis in there. There. That's normally how I do it. It takes a bit of time. It's more important for you to visualize than to actually graph. And that would be it for this section.